evening to you all. We, the Mission Coordination Cell, the National Quantum Mission at IIT Kanpur, welcome you all to another episode of the webinar series, Vision of National Quantum Mission, dedicated to exploring the thematic hubs that are shaping India's quantum technology landscape. In today's session, we will dive into quantum computing, T-Hub, established under the National Quantum Mission. In this episode, we'll unpack what makes quantum computers so different, why the world's leading scientists and tech companies are racing to build them up, and how this emerging technology could reshape the way we think about computing itself. The Foundation for QC Innovation, the Quantum Computing Thematic Hub at IISc Bengaluru, is a Section 8 company that aims to advance quantum computing and strengthen India's quantum ecosystem. Aligned with the vision of National Quantum Mission, it envisions positioning India as a global leader through the development of scalable indigenous technologies and a vibrant research and talent network in quantum science. Joining us for this insightful session today are two eminent researchers from the Foundation for QC Innovation, Professor Chandrashekar CM, the lead project investigator of the technical group Programmable Photonic Quantum Computing using qubits encoded in different degrees of freedom of a photon. He is Associate Professor at the Department of Electronic Systems Engineering, IISc Bengaluru. And we have with us Professor Chaudhuri, the lead project investigator of the technical group Quantum Computing with Neutral Atoms and Trapped Ions and Related Hybrid Systems. He is Associate Professor in Light and Matter Physics at Raman Research Institute, Bengaluru. Unfortunately, Professor Shankar Kumar Selvaraja couldn't join us today. He is the project director of the Quantum Computing T-Hub and who is also the lead project investigator of the technical group Photonics Quantum Processor Development. Our technical hosts for today are Dr. Gopal and Dr. Amrita, the technology managers in Quantum Computing Vertical from Mission Coordination Cell, and myself, Dr. Amrita, the technical writer from the Mission Coordination Cell. Before we get started, here are a few quick announcements. A feedback form will be shared at the end of the session, and e-certificates will be issued upon its submission. Please post your questions in the chat box during the session, and our technology managers will address them. We also request all to keep their microphones muted to maintain a seamless experience. There will be live streaming of today's session on LinkedIn, so please tune in. With this, let's get ready to understand how information acts in amazing ways that challenge conventional logic and hold the potential to transform our digital future. Over to you, Amrita.
And thanks, Amrita. A warm welcome to our distinguished speakers who join us today to share their expertise and insights. This session will cover three segments. The first session will cover a general overview on quantum computing, which will be followed by a little bit of technical discussion on different research activities being carried out at each TG. And then we will talk about opportunities, collaborations, and commercialization possibilities available at QC Innovation Hub. So let's start with our first segment, which is on general overview on quantum computing. Starting with you, Professor Chandrashekar, could you share the broader vision of the Quantum Computing T-Hub, its major goals, key deliverables, and how it plans to boost India's quantum ecosystem across different technology platforms?
Okay, so thanks for the question. And under the National Quantum Mission, the T-Hubs have been established with a very broad vision. So we should say it's a holistic approach where the multi-facet to it. First is to develop technology. So we need to indigenously develop technology. And the next part would be to develop an ecosystem, so which will enable the technology peripherals to be developed and also or what we call a human resource development. And and again, we also need, when I say ecosystem, it's also about the startups and industry collaborations and everything. So the T-Hubs is trying to approach this in multiple layers. The first one has been setting up technology group itself, right? So there has been 6 technology groups which have been formed from under the NQM, which is working under quantum computing. So now these 6 technology groups are focusing on different ways of realizing qubits, scaling up, and addressing various problems associated with different hardwares. And when it comes to human resource development, there has already been a series of program planned. Recently, we had a familiarization workshop where a big overview of the topic was given, and that was only a start of it. More such workshops and probably even in-house workshops to familiarize the topic in more detail is going to be planned. And then the other initiative has been to have internship programs so that we get more students, faculty members work with technology groups. That there was a call, and then there was also a close of calls. And there's been shortlisting of participants to work on it. And then there's now been a postdoctoral announcement, which is kindly what we call a QC bridge postdoctoral, where people can, it's again slightly a bit different from the regular postdoctoral thing. It's an independent research component. They can, they also get paid higher than the normal postdoctoral thing. And that's also kind of initializing or getting people into the field to learn more. That's again under human resource development part. The next part has also been startups. So where there was calls for startups to get involved with developing technologies. It can be a core technology related to qubit development, or it can even be a peripheral, quantum is a small part of the whole technology. You need a support system for it, and that's also has been there. There's been large number of submissions, and this also have been looked into. And at the next level is also getting involved with bigger industries, because we do want to develop technology within India, and we also want to be self-reliant on it. But we also want to expand to the world, right? Both ways, and we also have to learn from them, and then also have to give back to the world in bigger picture. So the big industry collaborations are also in line. So that's the way it has been visualized over the period of time. So,
okay. Thank you for sharing the insightful overview. I'm sure it helped our audience to understand the larger purpose of and impact of this initiative. Coming to you, Professor Chaudhuri, how would you describe the current global state of quantum computing? And most importantly, where does India stand in this landscape? And can you also comment on what strategic initiatives that can help position India at the forefront of global quantum computing race?
Thank you, Dr. Amrita. I hope I am audible now.
Yes, you are. Yeah.
Okay, thank you. Thank you for this nice initiative where we share the vision. And of course, this is a great question but I'll try to be specific and limit my answer of this discussion to hardware specific. So that means I will discuss about the hardware platforms related to quantum computation and how, for example, the global status and where India stands in context of the hardware platforms. Okay, of course, I recognize that there had been great progress in quantum algorithm development as well. And so that will be another discussion. So right now, I would like to highlight that the global development in quantum computing hardware is progressing at a very, very rapid pace. So there are many spin-offs and startups, and they are often led by academicians with decades of experience. Means if you look at the global structure, and they're having this expertise in controlling and manipulating quantum systems. This is not just a startup where the technology is being developed now. It has been developing in individual laboratories from the early part of this century, and even some of the industries who are now global player in quantum computing hardwares. They are initial situation where as a spin-off from global academic labs. So this is one thing what needs to be identified. And then for many years, photonic systems like Professor Chandrashekar have mentioned, and then trapped ions as well as superconducting qubits dominated the landscape of the hardwares. And presently, neutral atoms are also emerging as strong contenders. Semiconductor technologies are also advancing at a rapid pace for this global race of hardware platforms, which are becoming useful apart from the superconducting technology. India at present has a lot of enthusiasm to make similar progress. Many academic institutions, industry, and startups are working in this direction, hardware development. The introduction of National Quantum Mission is really making this progress accelerated, I must say, and we are seeing tangible effects. For example, India already possesses significant expertise in control and manipulation of various core quantum systems, including atomic and ion based systems as well. There are as many as 30 institutions and close to 200 researchers at various levels who are working for this development in India now. So they are directly part of the QC Foundation for Quantum Computing Hub. And there are many more researchers and also industry partners who are working kind of in silos at the moment, which we are aware of, and efforts are on to bring everyone on a common platform, and so that cohesive efforts for this development can be made. So what is needed now is this cohesive effort involving both scientists, engineers, and industrialists to design and build this complex quantum systems, which we will get into in more detail later on. So this requires strong multidisciplinary collaboration. I must highlight the fact that multidisciplinary aspect. I will say a few words about it. Now the bigger vision is that over time, this collaborative effort will only strengthen and develop the tangible results which we expect to come. So the thriving ecosystem, what Professor Chandrashekar had already mentioned, is very much needed strategically to actually progress towards this. So I wanted to highlight one fact that if you look closely, the quantum core of any quantum machine is perhaps only 5% of the technology hardware. For example, while physicists like us are handling this component, there are other 95% of the hardware which is still classical. For example, lasers and electronic components, ultra high vacuum components in many cases, and then the pumps, laser, electro-optics, and signal processing, which are largely classical in nature, and then developing strength across wider ecosystem, not just specifically making one quantum measurement, is very much needed to have a holistic development of this entire quantum hardware technology development. So this is one point I wanted to make. So strategies has to be actually developed so that there is a cohesive progress of both the core quantum as well as the peripheral so-called classical hardware development, which are very much needed for the quantum technology. Another strategic collaboration is between the international academia and industry for various joint development, which we must explore. But however, one needs to be careful in this vision, because at the end of the day, we would not like to become a consumer or even a service kind of a economy again in quantum. So we would really like to be in the manufacturing and in the production to avail the maximum benefit of this quantum age. And for that regard, collaboration with international partners is welcome, but then we should stay focused at the hardware development and manufacturing as well, so that the components are not just assembled. Whereas, so that is one of the core mandate and vision of the QC hub, that we develop hardware which are usable, and so the entire solution is provided through the hub. So these are the few points I wanted to mention about the strategies. Of course, there are various other peripheral aspects, but the core message or the vision here is the fact that a holistic development and an ecosystem which includes industry, academia, startups, which is also hinted upon by Professor Chandrashekar as well, is the need of the day for making quick progress here. Thank you.
Thank you, Professor. This was a really useful perspective, and it gave us a clear sense of challenges and also path forward. Thank you for that. So, moving on to our technical segment, Professor Chandrashekar, let's start with basics. So, before we get into details of photonics and neutral atom platform, can you please tell our audience what is quantum computing and how it is different from classical computing? And also, what are the essential building blocks to build a complete quantum computer?
Okay, I think it's a very important question because most of the time people do get confused that when we talk about quantum computer, it is an upgraded version of the classical computer.
Exactly.
A super classical computer. But that's not the reality. And this is a paradigm shift, a completely a new era. How I can put it in most simple words would be that, we all work in the binary world, right? The digital era we are is all zeros and ones. Everything is converted into zeros and ones. Even if I ask computer to give me an addition of 2 plus 2, it converts it into binary, it adds, and it translates back and gives me 4 as an answer, right? So now this binary system, which we use in classical computers, have been fantastic, great, but they also have a strong limitation. So let me give a simple example. When I say, if I want to represent 1, 2, 3, 4 numbers, then I can choose 2 classical bits. I can say 0, 0, 0, 1, 1, 0, 1, 1, right? Now, if I have to use them and do something with it at any given time, if I'm having 2 classical bits, I can only choose one of them, either 0, 0, 0, 1, 1, 0, or 1, 1. Like, that is my option. Now, if I'm taking a large number of even 40 classical bits, at any given time, I can only choose one string of them and do my computation, right? Now, that is how our computations are done in a classical computer. But what quantum mechanics taught us 100 years, we are celebrating 100 years of quantum physics because of all the theory formalism and first principles of quantum mechanics came into existence. Through some strange behaviors in nature. It's called strange, but it's a beautiful behaviors, which allows quantum particles, which when I say quantum particles, it's an atom or something at a subatomic level, right? When you start seeing things around the world in microscopic scale, it allows us to have things in superposition. It means it can simultaneously be at 2 positions. Of course, it does not happen in a very big scale, but at an atomic scale, we can see. Which in a simple words to say that, I can have an electron of an atom to be in superposition of 2 energy levels, right? It can oscillate between the 2. Now, that was initially considered as strange, but with over decades of experimental work, people have been able to see as this is the reality of nature, that it can simultaneously be in 2 positions. Now, instead of using that binary 0 and 1, if I use what we call this as qubits, right? Quantum bits, which means that it can be in superposition of both 0 and 1 instead of just being in 0, 1, 1. And now that is a fundamental chip. Like, okay, so what is so special? I can have 0 and 1. Here I can have superposition of 0 and 1. So, but if I have more than one such qubit, I can combine them together and simultaneously have it in 0, 0, 0, 1, 1, 0, and 1, 1. Right? When I gave an example of classical bit, I can only choose one of those configurations. But in quantum, I can choose all the 4 configurations to be present simultaneously. So which means that I can use all those 4 simultaneously to do my computation, which does not happen in a classical bit. I have to do it with one and with another, with another. It may not look dramatic if I'm talking about 2 bits of classical and 2 bits of quantum. But the moment I make 30 or 40 or even 50 quantum bits, then everything changes. Like, the 50 quantum bits, the number of parallel states I can get to do computation is almost equivalent to the best of the supercomputers today which exist. So that is the scale we are talking about, which a quantum superposition gives us, right? So now that itself make something like, oh, okay, if I really have a good 50 or 100 qubit quantum processor, I can do computation which the best of the super computers do. No, that is a theoretical, the numbers, and we know if we can have. The harder parts are there. Like, can we really build such clean 50 qubits which can do all of those things? And that is the task the world is on to, right? We want to build them and do. There is a lot of hurdles, difficulties that is there, but if we build something like that, it's, surpass all the classical computation. Now, this is what we see as a paradigm shift. It is not just an upgradation, which means that if I'm adding one additional qubit to a 50 qubit system, the computational power doubles, right? That is not the way what happens in the classical system. Adding one qubit additionally means doubling your computational power. It is because it is giving us the superposition states from the quantum computers. So this is the fundamental difference which we see from quantum computer. Now, qubits can't be just anything, and there are more, how can I recognize such qubits? How can I engineer them? Are the hard task which we have. That's probably the simplest form I can put as a difference between classical and the quantum computer. And this parallel processing capacity is what is giving you what we call an exponential, 2 to the power of, and if I take n number of qubits, the number of computational basis, what we call, the combination of zeros and ones I would have is 2 to the power of the number of qubits, right? That is what we're talking about, the exponential computational capacity, which we get with quantum computers. Having said the promise, the great, physically, the nature is showing us there is superposition. So we should be able to build, and there's nothing which could stop us to build. There should be difficulties to build them. So, or else something, in nature is not very clear to us. We might have to probe them further, right? So that's why as an academician or as a researchers, it is our interest that we need to build because nature is showing us it's possible. How we build, what are the hurdles? We have to, mitigate them with time. And everybody are looking at it. Just to give, might be there are few results which came talking about some supremacy claim. Might be recently Google claimed, or there is something from China a few years back. People are talking about 50 plus qubit. Now, this is where the catch was. Like, why 50 plus is something important? Because that's where they can actually show that it's probably classical computers. No classical computers can't do. Right. So it's not been easy. It's very hard, but the road is laid. We need to take the path and figure out how we fit in. Okay. So hope this gives some big picture. Maybe we'll be able to answer more.
Thanks for setting the foundation for understanding these advanced platforms. So staying on with you, Professor Chandrashekar, in photonics, the qubits can be realized in different ways, like through polarization, time bin, or even path encoding. So can you explain these encodings? How are they implemented and what advantages do they offer?
Okay, so I think just before going to photonics, when I said qubits need to be in superposition, so we really need to identify which are the quantum systems in nature, which we can isolate them and create them in that superposition, right? So now that would be the first one. And people have tried to look at various possibilities over decades. Right now, we have come to 5 to 6 of them, which are very promising, like can be superconducting, photons, spin, cold atoms, and ions separately. And so now here, even not just in photonics, even in superconducting qubits, there are different ways of encoding. Like now people use slightly different ways, but I'm not going to touch into that. When it comes to photonics, photons are among all the hardwares we talk about are most robust because it doesn't react to environment, which is like light travels long distances without getting disturbed too much. And polarization is there. Polarization is very easily controlled for people I've played around with for decades, even in classical light. So I can treat horizontal and vertical polarization as qubit, and any circular polarization would be my superposition state, which I was talking. Similarly, I can also control photon to be in superposition in time, which means that I can actually split them in time and make them be apart in time. When I make a measurement, it will either be here or here, but it is, if I've not made a measurement, it would be in superposition in time. And that's what we call as time bin encoding. And people have also tried to take them in superposition of two paths. And again, that is also possible. Now, there is a caution when you're trying to say, I can take photon in superposition in two paths. They should be within coherence. It is not like, I'm not splitting photon here. You can't split a photon. I'm trying to take them in superposition, which means that it's in both the places. If I've not made a measurement and there's some coherence length with which we have to work with. And those coherence depends on the uncertainty of photon's position. If I have some 10 photons position, spatial width of some 10 nanoseconds, then I get up to some 3 meters of width of coherence length. So it means that there is some space which I can keep photons in such kind of superposition. So these degrees of freedom are very handy with photons compared to other hardware. I can actually manipulate them easily. I can take classical polarizers, or there are some beam splitters. Or the difficulty is getting single photon, but given that I have a single photon, I can create them in such kind of states. So people have done it for years. That's why you can always encode them. In communications, they are extensively using them, all the encodings, because it's easier. In communication, you just have to send single bits of information in line, right? But in computation, we need to combine them. As I said, I need to create multiple qubits together and make them interact. Now, that has been a major drawback with photonics. I know you can't make them interact. They don't interact with the environment, neither they interact with themselves. So that has been one of the hard to create a 2-qubit gate operation, so to call. But the single qubit encoding has been well established for decades. I think there's no debate over it. People have played around with implemented single qubit gate operations and practically built devices, communication devices, both in India and abroad. And that's something which is very interesting with photon. You can actually combine them. You can independently combine different degrees of freedom, and you can engineer them at the single photon level. And that's something which is more handier in photonics compared to other hardwares. In other hardwares, you may not be able to use multiple degrees together. You can either use like in superconducting, transmon qubits, what we call, or we also call about currents are used as qubits. But you have to either choose one of them. But in photons, actually, we can even combine them together. People have done a lot of experiments in that direction.
So, can you also talk about your recent achievement? You recently achieved a 6-qubit entangled state using only 2 photons. So,
Okay.
can you walk us through that?
Yeah, I think, in the beginning itself, photonics was considered as one of the promising candidates because of you can control degrees of freedom. But the major challenge which came was, how do we make 2-qubit gate operations? Mm-hmm. And people came up with probabilistic approaches, which means that to take 2 photons and make them interact, I need to bring in a third photon as an what you call ancilla, so that you make the third photon interact, and then you do a 2-qubit operation. The moment you make a 2-qubit operation, the success rate used to reduce. So it means that if I have to build a quantum circuit with some 10 2-qubit gate operations, the success probability of computation was going down significantly. But however, people thought photons are still free, they don't interact with it, and that is still promising approach. One of the big questions which they asked, can we reduce this probabilistic nature of 2-qubit gate operations? So the idea of using different degrees of freedom in combination was floated around, and people are, I think right now, 18 qubit entangled state using 6 photons was shown by Chinese group in 2018-19. They used 3 different degrees of freedom. But what they didn't do was they didn't implement gate operations, 2-qubit gate operations. It was one specific way of creating square. But for us, we wanted to build 2-qubit gate operations. Actually, 6-qubit is an output of it. Our main result was focused towards implementing deterministic 2-qubit gate operations. So we choose photons, polarization degree, and path degree, because you're not dealing with 2 photons. Then I can do a controlled operations and implement a deterministic gate operations, because the moment gate operations become deterministic, at least to some level, then the computation success rate would increase in photon. And that was our core motivation. We had developed theory for that few years back itself, and we were trying to look for options to translate into it, and NQM came in between, and it kind of made our model realizable in a laboratory setup, and we could successfully demonstrate all the gate operations. When I say, okay, you have built demonstrated gate operations, what next? So we put them all together and then generated a 6-qubit entangled state. And goal of this 6-qubit is a deterministic. There are certain catches here. Can I now just take 2 photons? We took 2 photons and build a 6-qubit gate. Now, can I just 2 photons and make 20, 30 qubits? It's not very practical to scale similar way. I need to work out a combination of, I bring in more photons, but I can still realize larger number of qubits. So we have architecture developed for it, and we try to see how we can, and we have different ways of plan to scale up the number of qubits. But this has set us some grounding now, and because we have been able to demonstrate gate fidelities of more than 95%. In bulk optics, that itself is very good for us, a deterministic gate operation. And this was also the first time anywhere in the world where you could actually demonstrate all the 1 and 2 qubit gate operations using these 2 internal degrees of freedom. So yeah, we have challenges. It's not just linear challenges in research. So we have to mitigate them, but this is a good first step for us.
Thanks, Professor Chandrashekar. It is impressive to see how such innovative experiments are pushing the boundaries. We would like to know you from Professor Chaudhuri. Can you please explain how qubits are realized and controlled in neutral atom or trapped ion systems? I believe that neutral atom and ion trap platforms share similar architecture but differ in interaction mechanism and control methods. So can you also elaborate on their respective strengths and weaknesses?
Okay, right.
Over
Thank
to you.
Yes. So in both neutral atoms and trapped ion platforms, the atoms and ions are confined in free space using electromagnetic waves or time varying electric fields. For example, in neutral atoms, the atoms, each individual atoms can be confined in a tightly focused laser light. So which is also known as an optical tweezer. So it's like a standard tweezer to pick an object up. So similarly, if you very tightly, we are talking about focusing the light to the wavelength, to the west size of the order of a wavelength. So this is not a very, very straightforward job, but with development in modern technology, this has become routine in the laboratories. And once we do that, there is one single atom inside such a single optical tweezer. And then the technology also allows us to create an array of such tweezers. So you need not have to focus one laser light in one space, but you can have neighboring spaces, for example, separated by around 5 micrometer. Tightly focused laser light. This laser light array is generated using a device called spatial light modulator in our lab, and then focused using very high numerical aperture objective lenses. And then each individual atom inside optical tweezer will act as a qubit. I'll elaborate a little bit how this happens. So, for example, ions can also be trapped using the specific arrangement of the electrodes, where you can apply time varying electric field to the electrodes and they can get trapped. Of course, in room temperature in the environment, one atom can get trapped or one ion can get trapped, and that can be knocked out by another atom or ion which is moving past it. So this needs to be done inside an ultra high vacuum environment where there are no other or very few such hot atoms or hot ions. And then there is another technology we make use of, which is called laser cooling of these atoms and ions. We shine a laser light very close to the resonance of these atomic systems, or even in case of ions. And then this laser light is cleverly used in such a way that the extra kinetic energy of these atoms and ions are taken out by the laser atom interaction itself, the light atom interaction. So by doing that, we now have a bunch of atoms or ions which are in space, perfectly ordered. And if you end up trying to make their temperature, they are of the order of microkelvin, which is unimaginably low temperature, which is far, far lower temperature than even liquid nitrogen or liquid helium. So this is like very close to absolute zero. And in that context, as Professor Chandrashekar said, the atomic energy levels or ion energy levels, the atomic state can be in a superposition of various energy levels which are available. So now this becomes a realization of a atomic or ionic ion crystal. Ions together with these, once you cool them down in presence of the Coulombic interaction between the ions, they also naturally crystallize to have a kind of special arrangement. So you can try to scale that number, and we can have now, for example, one of key member investigator in our group, Professor Umakant Rapol from IISr Pune, they have recently demonstrated a very high number of such ion crystals which can be individually manipulated by focusing laser light on each individual ion and so on, and making oscillation between one ion state to another ion state. For atoms, for example, we at RRI and various of our member consortium institutes in NICER, Bhubaneswar, IIT Guwahati, IIT Roorkee, we are working on and making progress in trapping individual atoms and scaling up the number of atoms in individual traps. And we are already able to successfully cool down the temperature to the microkelvin level, where the individual atom quantum state manipulation can be done in the lab routinely. We have been working on this system. Now, so going forward, this atom array or the ion arrays can be used as a entangled source for not only single qubit gate operation, multi-qubit gate operation. Here, one of the key requirement is to introduce interaction between the atoms. So in case of atoms, this is done using Rydberg excitation of the atom. For example, at Raman Research Institute, we do have other research groups where Professor Sanjukta Roy and her team have demonstrated that in a collection of these atoms, if you create Rydberg excitation, then you can make these atoms go to very highly excited state, and then these becomes strong dipoles. And once these dipoles are brought near to each other, this dipole-dipole interaction actually helps in creating very high degree of quantum entanglements between atoms. And that can be used, for example, in atom number 1, if a quantum operation is made to go from state 0 to state 1, there will be a quantum correlated state preparation in atom number 2, which is entangled with that, and that so-called quantum resource can be utilized for the implementation of various quantum algorithm development. Similarly, via Coulomb interaction in the ion crystal, similar entanglement strategies can be developed, and then the 2 and multi-qubit gate operations can be done. We are working actively towards this direction so that multiple quantum algorithm gate operations can be implemented for useful quantum computation as well. Now, the next part of your question was that what are the key difference between atoms and ions? They share a lot of technological similarities. For example, in case of trapped ions, they are also confined in ultra-high vacuum, as I said. So when I say ultra-high vacuum, that is actually a technological challenge that typically the vacuum environment required is at 10 to the power minus 10 to minus 11 millibar pressure, which is like 13 to 14 orders of magnitude below the atmospheric pressure. So that requires careful arrangement of the vacuum components and the sources, and making sure that the laser light is passing through the optical windows and so on. So this is done. And then the same story is true for atoms also. However, in case of atoms, there is an external control of these trapped atoms by moving around the optical tweezers, which are typically focused laser light from outside the vacuum system. In ions, this is a little bit of a design constraint, because how you actually have designed the electrodes which have been inserted inside the vacuum chamber, and then you apply voltage, kind of dictates what are the number of ions and the spacing between them, what is the degree of entanglement created. So then both ions and atoms, the mechanism for qubit operation is via very highly tunable and small line width laser, which is interacting with the atoms and transferring their quantum state without knocking them out from the trap. So this is a delicate operation. Once this is done, the fluorescence, that photons which are coming out of these trapped atoms and ions, are collected onto EMCCD cameras, and then from there, their state operations and state detections can be done. And this way, every realization of a quantum gate operation can actually be observed on a detection device like the camera. And so there are some few other key differences. For example, in ion traps, there are very high storage time. You can trap an ion, and then since it is in ultra high vacuum environment, you can leave it there for hours and even for days, and then keep on doing quantum operations and so on. Atoms are a little fragile. Though in the lab we routinely show something of the order of few minutes of storage time, but on the other hand, for the time scale required for any quantum operation, so this is typically done by pulsing laser light, which we call pi or pi by 2 pulses, so which actually makes the superposition and makes the detection of the superposition states and so on. And those time scales are typically of the order of in microseconds or so. So in both cases, whether you have the trapped lifetime of the order of hours or minutes, this is sufficiently long enough. But challenges are that you have to do this operation not on one single atom or one single ion, which is interesting, which is fundamentally giving information. But for doing practical quantum algorithm implementation, you have to do this in a series of collected arrays, and those arrays has to be defect free. There should not, for example, be one atom, another, and then a blank space and another. So these are practical challenges which we kind of overcome by moving around these atoms using movable tweezer traps, using devices called acoustoptic deflector, where sound wave on a crystal makes the laser light shift around as and when we do, and they also drag along these atom qubits and to place them in a perfect array or a perfect grid. So we call this like a defect-free array mechanism. In case of ions, one has to be very careful that how this ion crystal is entirely stable. But these are the technical aspects. But once they are taken care, then there are viable scaling pathways. For example, increasing the total number of tweezer array is now a matter of technological development. How much laser power I can spend, for example, when I am creating that array in a 2-dimension, how good I am able to detect this array using my microscope objective onto the CCD camera without losing the detection fidelity for the atom which is at the center of the trap and for the atom which is at the periphery of the trap. So these are the questions which practically pushes for the technological boundaries to scale the total number of qubits. But as a nutshell, the number of qubits are how many such atoms you can trap and simultaneously detect, and same story for the ions as well. So I hope that I could give a little bit of technological overview to these aspects.
Thank you, sir, for comparing the two systems and giving us a technological overview. Staying on with you, Professor Chaudhuri, what is unique about a hybrid system combining neutral atoms and trapped ion? And do you see a potential or ongoing efforts to interface it with photonic platforms?
No, this is great because, so as I said, that the neutral atoms technology is these arrays of atoms, arrays of single atom. For example, it is not really very much helpful if in one tweezer there are more than one atom, but there are ways to take care of this problem. So that various blockade mechanism, quantum blockade mechanism helps us so that we ensure that there is one atom. Now, the neutral atom, particularly I work with neutral atoms, so I first wanted to start with an advantage. So that they are also great for what is called analog quantum computing or quantum simulating. For example, you can create a particular array, particular geometry, and this becomes like a Hamiltonian of the system. And you can look, for example, in response to the interaction between them, which is tunable, by the way, by external changes in the electric field, magnetic field, as well as the laser fields as well. And then one can look for the time evolution or unitary evolution of such quantum system. And once you take such a system evolution and take one picture at a different time, so this directly tells us about a quantum system evolution, and which has various similar for example, the molecular dynamics or even financial market. Various evolution technologies are similar. So these are called analog or quantum simulating, which is one great way. In case of ions, these are very well suited for what is called universal quantum computing or gate operation. By the way, even in neutral atoms, there have been good demonstration over the past couple of years or so globally and more that the universal computing with multi-qubit gate operations could be demonstrated very well. And ions, some quantum simulation can also be demonstrated. So both platform has pros and cons having a wider applicability. And now either the results which can be analog simulated or universal computation can be done in one integrated system, be it in one integrated hardware where both the ions and atoms are present, or separate hardwares which are connected via the same series of electronic investigation or the laser pulse and so on. So actually offers a hybridization or integration platform as well. Moreover, I wanted to highlight the fact that these eventually becomes quantum circuit implementation. And now one doesn't have to be limited to a quantum circuit implementation in just one platform, but in a hybridized system. So this is one thing. Another, so far globally and even in our technology group, we are working on this optical tweezer array, or the investigation with the light pulses addressing the single atoms or ions, which is spatially resolved and so on, by light sent from the outside of the vacuum system. Okay. Now, photonic platforms, which are integrated photonic designs where they can be coupled inside the ultra high vacuum system, where the light can be coupled into them via the optical fiber technology, can actually do the job of creating both arrays and the investigation of this atom and ion array. So a hybridized system where the photonic platform works as a trapping or the light delivery system for the trapping and state detection, state manipulation, as well as the atomic physics package, which is taking care of the detection and then manipulation of the atom array and ion array. So that holds a great future, because once you have a miniaturized photonic crystal. Of course, this is easier said than done, because the wavelengths which are required for manipulating or trapping these atoms and ions are typically in the near infrared or even in optical domain, whereas various photonic technologies work at a reasonably deep in the infrared or telecommunication wavelengths and so on. But there have been global efforts so that those engineered photonic circuits can actually be inserted, and there can be a good marriage between the atomic and molecular physics community with the photonic system, so as scalability. For example, the larger number of arrays, the faster manipulation, and also higher fidelity can also be explored. So these are some of the highlights for ongoing effect to interface with the photonic platforms as well. So where a photonic platform will provide a better architecture for the trapping and manipulating the individual atoms and ions. And in that case, we will be using the photonic platforms more as a platform to create the trapped arrays and detection systems and so on.
Thank you for that thoughtful perspective. Though you have given us some hint, but Professor Chaudhuri, would you also like to comment or give us more detail on the use cases of neutral atom ion computing platform? Mm-hmm. Also, Professor Chaudhuri, how do you envision commercializing the neutral atom or ion-based technologies being developed in your technical group?
Okay, so this question really has two parts. One is the use cases. So as I said that there is great potential for the analog quantum computing or quantum simulating, going beyond academia, where there is a lot of interest of analog quantum processing from the condensed matter perspective, from the molecular dynamics, as well as finding similarity of the evolution of a particular system. One example comes to my mind is for example drug discovery and so on, where various analog and quantum simulation has been proposed and being taken care of. And the other aspect of using the neutral atoms and trapped ion as an universal quantum computer will share the same use cases, for example, in various other technology platform will also offer, for gate operations, quantum algorithm implementation. And one point I have to say is that there is an impressive conversion of the physical qubit to the logical qubit in case of neutral atoms, where quantum error correction algorithms actually work very well. So that, if I, let's say, trap an array of X atoms, let's say it's 400, it is easy to actually make something like 50 logical gate with error conversion efficiency going 1/8 to 1/10. Which is one impressive direction, where then one can use those logical qubits for making various universal computation, which Professor Chandrashekar also already indicated. Those use cases will be very similar, and I would also like to say hardware agnostics. For example, when you try to make a particular algorithm, whether you are running this on a photonic platform or a quantum platform provided by ions or atoms, they will be very similar. So both the universal, that also sometimes is called digital quantum computing, and the analog as well as quantum simulation use cases can be taken, and industries such as financial technology, drug discovery, as well as industries which are looking for sorting algorithm, which are even cases of security, where various security algorithms can be implemented, where the neutral atoms and trapped ions will have great this thing. So this brings us to the commercialization aspect. So we are quite proactive from day one. From our TG, we do already have one startup which is registered, and we are looking forward that users and interested future clients can connect through the startup, so that algorithms can be run on such platforms, perhaps in a few months time scale and so on. And moreover, the hardware scalability, for example, just having one or two or maybe 5 hardwares available to us all over the country is not going to serve the purpose, which can be very nice for technology development and so on. But on the other hand, there needs to be also off-campus installation of these hardwares as well. So the commercialization aspect can also be in having various installation off campus, which is perhaps in phase 2. We are very much interested that once the platforms are stress tested, as well as users connect with us via the startups which are already acting on this, as well as more startups who wants to join with us, where there might be specific expertise of a startup having, a particular healthcare related algorithm development, who can then, convert the use for get of series of optical and atom ion platform based algorithm implementation, and we will be very happy and open for such opportunities, so that it can be a win-win situation where the commercialization aspect can be implemented directly. So we are really looking forward going beyond academia, going beyond fundamental developments in scalability, etc., but also what we will have very soon, or what we already have, whether this can be usable, where the commercial interested people can be use through, of course, the National Quantum Mission, and so that there is a almost immediate impact which can be created. So that is where we are actually having the general vision from our TG, that how the commercial aspect. There is also another aspect which is in training, that of course this technology requires the hands-on training for the people to eventually make a replication as well as do that. At present, we have a very limited workforce who are trained in not just assembling or developing, but also executing such systems. So commercialization can also look forward for having a larger training knowledge-based creation, so that there is a accelerated development in future.
Thank you, Professor Chaudhuri. It is great to know such interesting research and its outcome. Now, switching back to you, Professor Chandrashekar. One of the TZs in quantum computing T-Hub is working on integrated photonic circuits, which are considered vital for scaling up quantum technologies. Could you please tell us what PIC is and its importance for building larger and more scalable quantum systems? Can you also comment on how close are we achieving fully integrated quantum photonic chips?
Okay. So there are many aspects to photonic quantum computing. As you mentioned, photonic integrated circuit is one of the most promising way to scale the computation. In fact, there are people who are promising that within some time we can even go to millions of qubits with photonic integrated circuit. Why? What is the reason for them to talk about such big numbers? Is that it's just like an electronic circuit, right? When you have an electronic circuit, you have electrons moving around. You are going to get current, and most of our signals are to electrons. It's the same way. You can have some silicon based materials. It's like waveguides where you can guide photons to pass through them, right? So now that's something which people have been working on for many years. Waveguides are there. Photons are made to pass through them. But then the problem now comes, the next level is that how are you going to control, right? You need to do some, operations on them. I can take a small, material, silicon based, and draw some thin lines on them and make photons pass through them. But now I need to control, I need to change the directions, or I need to change the polarization, and all these questions comes in. But the problem again has been the stability of photons in such kind of materials. So polarization don't survive long in such kind of material. But people have been trying to work on different possible kind of, dopings for such kind of silicon material so that polarizations can be maintained. And some progress have been there, but not very promising. But there are, now you need to even control, there are some electric currents which have been passed through at what we call as, you can control the waveguide's paths. Some shapes of the waveguides can be modified to make them split, and all this external control can be introduced. If you can do them, then it means that it can be programmed from an external, drive force. The photon paths can be controlled, and you can do some gate operations. You can make them interactions. So that is what we call, as a photonic integrated circuit. So now, where do we stand, and how, even globally? You need a heavy foundry, capabilities to do such kind of design, right? I mean, I can't have a small lab where I can't have some small thin millimeter lines drawn, and then so there are some, there are facility which exist in IISc to do it at some small scale, and there's also other places in India. But to scale them to a large extent, we might have to develop an additional facility to look at it. But that's one part. But then again, now, what kind of schemes, like what degrees of freedom can be used on photon integrated circuits are always a big challenge. People have been trying to come up with, even there are recent developments of using polymer based materials where you can actually do a 3D printing on them. Polymer based material can be 3D printed on which you can actually guide photons and do some gate operations. It's a very early stage. But people are thinking that if that's going to be very, practical and scalable, then that might be a very good platform to look at it. The TG in IISc, which is headed by Professor Shankar and a few other collaborators within IISc, are trying to come up with a completely integrated platform where you have a source integrated into the photonic circuit itself. Right now, a single photon source. In my earlier discussion, also I didn't specifically mention that. I talked about, you have a single photon. After that, what you do? But how do we get single photon is always a big challenge. My lasers will have billions of photons or millions of photons per second. So there are a couple of ways which is reasonably established. One of the most well established is what we call as a down conversion, which means that I shine a lot of millions of photons into some crystal. That crystal down converts 1 in a million of photon into pairs of them, which can be isolated as single photons, and most of them don't get down conversion, which we call as parametric down conversion. And this is one of the most well established techniques, and that's what we use in our TG for the time being. But now those photons can also be guided. You can guide them into a photonic integrated circuit. You can do operations. But then the source will not be something which can go on a chip. So you need to have a source separately. But then people have looked at that also very reasonable option. You can actually generate a source. You can guide them into a chip where you can, make photons go to certain paths, do an operation for you, get it out. When you take it out, now that comes the detector part. Now detectors are also a bit bulky because you need to have a single photon detector. There should be electronics associated with it because they don't detect noise. So that's one of the approach. But an integrated approach, which other TG and IISc is also trying to look at is, can they, they're trying to come up with a source which can be integrated into the chip itself using some four-way mixing and or even quantum dots approach. In quantum dot approaches, what they try to look at is there's some specific materials which you can shine light in some direction, and those dots emit single photon. Now, there's still not yet in room temperature, and the single photons are not the very purest form which can be efficiently used for computation. But that is also another promising approach because when we know science, the way it develops, there is always some hurdles. There's no it may not be clean, but we know that there can be made a clean photons, and they can you can actually improve the temperature at which it can look at. There's a promising direction. So if you can integrate source into the chip, then you can also think of integrating detectors into the chip. It can be a small sensor which can sit on the chip, which means that if source and detector sits, whole part can be made and integrated. Of course, you might have to have a controlled electronic system outside and all of those things, but still the computational process can be completely integrated. So this is something which has been a promising approach, and probably that is the only way to scale to larger number of qubits in photonics in long run. When we talk about bulk optics, either I said about 18 qubits, which China did, or what we did at 6 qubits entangled state generation on gates. These are to demonstrate that how it can be done. And, in bulk optics, we will see how the photons path can move to and what control has to be done. Once that is established, then we have all the parameters which will help us to design an integrated circuit, because you can't directly just design them. You need to first have a mathematical model, and then I have to have tested it in some scale. We have current, and I know, for example, when I said we have achieved about 96% fidelity, it's mainly because we need to make a single photon go in superposition and again come back and interfere. When I'm talking about interfering them, which means that I'm talking about a nanometer scale or a micrometer scale precision of the path length, right? Whenever I'm using any laboratory bulk optics, I can't have that engine. A small wind in the lab or some small blow from AC can disturb that path, and you're not going to get your result. Now that is where photonic integrated circuit is going to help me. If I can design the path lengths up to that precision, and if I'm just maintaining the it can be room temperature. You should not have fluctuation. If I can maintain the circuit or a chip in that room temperature, because room temperature would change the paths. If I say from 28 to 32 or 28 to 20, which means that there might be some disturbances in the path and I may not get the result I want. But if I can maintain some standard temperature, then the interferometers is what we call, can be very efficiently achieved in photonic integrated circuit. And if one can have hundreds of interferometers built, which means that you can actually have hundreds of gate operations easily implemented on a photonic integrated circuit. Just getting one thing right and then replicating them will always help you to scale. And probably that is what one of the strong reasons for people who are working on photonics to see that, you can, once the science is established, once the protocols are established, then it's just a replication and scaling into, thousands or millions of qubits. So, but the challenge has been not with integrated circuits as such, or not with internal degrees of freedom. How do we make them interact and do the gate operations? Because how much additional resources you have to do. And probably that is one small bottleneck which people have been, working on in photonics. So there is not, when we're talking about different hardwares, I think what I didn't mention earlier also is that there are different approach for computation itself, right? We are not gate-based. When we talk about gate-based, that's still one part. Even in gate-based, people have different schemes for it, right? In photonics, we have a continuous variable approach, what we call as something we don't deal with the single photon level. You can use coherent light and you can split them also and behave as if they are two superposition states. And then one is a discrete variable approach, what we follow in our lab. We take different degrees of freedom, clearly create a qubit out of it, and then do. There is also something called as fusion-based approach, or even a cluster state approach, where you create a multi-photon entangled state. Creating is very hard, but if you create them, then you can make some partial measurements on them, which will be equivalent to doing some gate operations, and you get a result output. So this is also one of the approaches, creating a large cluster states or multi-qubit state, multi-qubit entangled state is something which people are trying in integrated circuit, rather TG. But there has been some good progress, the detectors, because single photon detectors are very important. There's a research group in IISc which have been looking at it for a long time, and they have been able to make some progress, but to have indigenously develop some sensors for it. How they are going to now engineer and make it get and sit in the integrated circuit is an important task, which has been taken up under the mission. So source is being developed in IISc, which can go inside, and detectors also has been developed, and the circuits have been planned as a part of the mission, the teaching. There.
Thank you, Chandrashekar sir. It is very interesting to know how PICs are contributing to reliable quantum systems. With this, we come to an end of our technical segment. This is indeed a good resource. I think many of us will like to listen it on repeat mode. So thanks for that. Before moving on, a gentle reminder, feedback form will be shared at the end of the session, and e-certificates will be issued upon its submission. Please post your questions in the chat box during the sessions, as you are already doing, and our technology managers will keep addressing them. We also request all to keep their microphones muted to maintain seamless experience. Now moving towards Amrita.
Thank you, Gopal.
You can.
Yeah, thanks. So we have come to the last segment of our today's session, that is opportunities, collaboration, and commercialization possibilities. So coming to you, Professor Chaudhuri, for students and early career researchers interested in quantum computing, what are the key opportunities or pathways in Foundation for QC Innovation to get involved or contribute?
Yeah, so that is one very important aspect, because when we say building ecosystem, one of the major roadblock is to have trained manpower. And we are also very much keen that we take care of the training and so on. For example, recently through the Foundation for QC Innovation, IISc, there had been a series of talks by practically all PIs. So it was nearly a week-long session where both myself, Professor Chandrashekar, and many other PIs have presented detailed technology presentations and so on. So people have very enthusiastically attended such sessions, which is very nice. We are also very open that interested students do write to us, visit, because there are also opportunities which are being posted on the websites, both the QC Innovation website as well as individual institute website for all the JRF, SRF, postdoctoral and research scientist positions which are open, and so that people can directly connect and join with us. And we will be very, very open with such opportunities. However, so there are multi-pronged approach. One is that in the laboratory, there can be only that much opportunity for people to connect and really do the hands-on work. On the other hand, the initiatives for teaching and workshops, which we are regularly doing. For example, our technology group has already done 2 technology group workshops where young researchers have indeed joined. One was done at RRI, another one was done at NISAR Bhubaneswar a couple of months back, where we are getting into brainstorming discussions, and people are being part of the training and so on. So this is one way. And as I mentioned before, that there are also other researchers who are working very, very deeply in the quantum technology development. And if there are overlapping interest, and this will be a request through this webinar series, that people can try to join with us. We'll be very happy to make use of all the available expertise. So I do also see in the comment section that there are lots of interest in people who have done algorithm and various other exposure to the quantum technologies, to also see that whether there is an opportunity for having joint developments. And yes, indeed, that is true. And through the hub, through the MCC, you, and also individually writing to the PIs and the team members, there is a great opportunity for joining in. Going forward, I am sure that the efforts of taking up more such quantum computing bridge fellowship and so on will come up, where researchers at various stages of their career can actually apply. And one request would be for everyone to keep an eye on all the websites which are relevant, so that we can get communications almost immediately. Because sometimes I have seen that people have written to me when the deadlines of the applications were over. So we have difficulty in handling such situation. So keeping an eye on the websites will be very, very useful. But this will be repeated in cycles, announcement for opening of positions, as well as the collaboration and with the industry. And as I mentioned that we are already in talks with various software industries and agencies for collaborative approaches. And we can only say that not just me, but also all the PIs are very, very happy to discuss for any ideas which are coming, because it's a national mission. So we have this broad vision rather than having a very specific collaboration. So and whatever is possible to have these opportunities for young researchers and enthusiasts, we are very open. And so there are already announcements, but more will be done, I'm sure, as we receive more interest and more inputs from people.
Yeah, thanks, sir. And it's great to hear we take such initiatives. And I hope the students can take advantage of the opportunities available at the hub, and do follow their website for the updates.
Just wanted to add that, there are also individual initiatives from various institutes. First of all, in response to International Year of Quantum, as well as after setting up of National Quantum Mission, and PIs and researchers are actually traveling and giving seminars. I have myself done that, and so this also gives awareness to various, not just IITs and IIScs, but also engineering colleges, degree colleges, and so on. And this also is one opportunity which we would like to announce, that we will be open for such sessions as well. Of course, it will be great if it is done through the MCC, the Mission Coordination Cell, because in that case there will be a good way that this can be a tab can be kept on that how many such initiatives are happening. So I just wanted to add that as a possible awareness drive and technical availability of the researchers.
Thank you, Professor Chaudhuri. I hope the audience can take note on that and act accordingly. Thank you once again. Coming to you, Professor Chandrashekar. Looking ahead, by the National Quantum Mission reaches its goal, and what kind of real-world applications or problems do you see that the quantum computing platform is being able to tackle or make a real difference in?
So when I say National Quantum Mission goal, so we should say that the goal has been set for something, but the evolved technology is a big evolutionary approach, right? So when we're talking about 6 different TGs and 6 different hardware, which means that clearly all of them are a very good candidate, and all of them have their own advantages and their big drawbacks. So, which means that there is still a lot of room for new thing to come in. Suddenly, some big new scientific results can come in and might improve one thing significantly, and others could be used for something else. So, this is also under under our purview, right? We are not going to just set some goal and then you're just going to keep going at it. The goal has been set so that we have some specific targets to reach across the hardware, and then indigenously developed technologies, because there are 2 things. It doesn't matter whether I'm working on photonics or I'm working on cold atoms or superconducting. What we are learning here is how are we going to build things from scratch? How are we going to understand the hurdles which we are going to get? And the awareness is there at the technology development level and at the usage level. So that will help us to adopt significantly, right? It doesn't matter if some new things would come in, then we have a know of it, like how to do things and how to manipulate, and we'll be able to adapt. That's one of the biggest thing which mission is going to is doing us. The labs are getting prepared. The ecosystem is being developed so that we'll be able to develop or like adopt to the system. Now, coming to goals, each TGs have set certain goals. There are some scientific development goals, and then there is also technology development goals. Either it can be achieving number of qubits, because the numbers is a very small story of it. I can always pick some numbers. This is the number of qubits we are going to look at it. But the most important thing, as I said, what is the usability of it, right? Like, how am I going to use them? Whether it's just going to be for some demonstration purpose, or are we going to use it for some applications, and how can we scale them? So both things comes into the picture, right? So now, let me first say about our TG's particular task. So the way each hardware, as I said, there are some advantages. Photons work at room temperature. I really don't have to, carry cryogenic system around it. So even building a smaller number of qubits could have some applications. We did do that sometime recently, is that we had just 2 qubits and we could build an entangled certified random numbers. So it's a device, right? It's a portable device. We have moved around different cities, and it's currently being used in a few government organizations to generate keys. Where are these keys used? You can have OTPs generated from it. You can have your VPN codes generated from it. How is that different from a classical computers? Also generates them, but they are pseudo keys. You write some codes and then you can generate, but now quantum devices are generating from the principles of quantum mechanics. So there is some kind of cybersecurity associated with it, right? You are not relying on any software to give you keys. You are not relying on any vendor to give you keys. You can be a nice vendor, or you can be a vendor who is trying to trade off the keys to you and then to some others else also, right? In that way, even smaller number of qubits, which we are indigenously developing in the country, would have some applications. So 2 qubits, something like that we did. Even in 4 qubit, we could actually generate a public and private key. And we are trying to convert into device which can be used in banking sectors, right? Everybody needs public and private keys. Now, these are a simple applications from a smaller number of qubit devices. So we are not all still, anywhere halfway through the mission also, but we do see some small scale cybersecurity applications with photonic devices. It's not just with my TG. Now, this is trying to say that even people who have not been directly part of mission, but they're indirectly part of mission or any labs, can always think of such kind of applications with this. Now, there are algorithms which we talk about, variational algorithms or hybrid algorithms, which also can be, tested with smaller number of qubits, which people are trying to build. And this will all be within the purview of National Quantum Mission in next 1 to 3 years, while we are still going on to completion of the mission, or like whatever the end goal. So there has been efforts from all the TJs to think of what you can do with smaller number of qubits. Both one, it can be a direct device development, a translational device development, or it can be a central facility where people Professor Saptarishi was mentioning about having somewhere and then giving an access for people to work on it. It is not just academic institutes. Like, for example, the way it has been in the initial also I said we are doing an holistic development. Many TGs, including our TG, are tied up with other organizations. Like my research group is tied up with Center for Development of Advanced Computing, which is developing our own software for the hardware which we are building, right? Because each hardware have different ways of connectivity and how we are doing gate operations. So they have built some QUniverse, which is a universal software package, and now they are building a hardware specific interface so that you can actually put them on a cloud. So the whole by the time we are reaching even closer to the end of the first phase of the mission, we should be able to have hardware at some particular place and then an indigenously developed software control system sitting in some other organization, and universities and colleges having an access to them so that they can write their codes and then use it. As that itself is a first level of accomplishments under the mission, because we are not dealing with any industries here. It's just the path of or it's the plan of the mission itself, so that you are integrating a research group with another government agency which is building software, and they are talking to universities where they can access and play around with the system. So and that's the part of the smaller user cases, which Professor Saptarishi mentioned, that the approach is not hardware specific. You are trying to if you're building a universal quantum computer, which means that you are making it independent of the hardware, right? You need to develop a quantum circuit. But there's another important aspect which goes with every hardware is the mapping of qubit. Either it can even be, any companies which are building qubits, there are connectivity issues, and not everything are connected. Everybody are building their own architecture. Nobody knows which would be the most ideal one and what connectivity. Now, each connectivity has to be mapped to some software, and that has to map to an algorithm and to the math associated with it. So there's a full loop of the control system, an integrated system to be developed, and that is also is something which will be there as an end product under the mission. I think all the hardwares are trying to have such kind of interface developed as a part of TG. Commercialization, I think there has been quite a lot of effort, which means the mission itself is trying to bring in one startup support has been separately planned, independently planned, and there is also a startups being associated with TGs, so that intermediate technology has been developed which should be translated. It doesn't, at the end, if I just say we have done some 20, 40, 50, 100 qubits, whatever it is in each of our labs, if it's not translated into a technology, then the effort may not serve its purpose, right? So we need to translate it into a technology with the help of industries, and that's something which has been initiated on the mission. And there has been evaluation of TGs where we will have to have a plan regularly updated. We have some plan initially proposed, and we need to come up with the way dynamically get industries involved, so that the technology has been translated and the devices will be available for a practical use at a different scale.
Thank you, Professor Chandrashekar. Hope you achieve exciting outcomes that can truly be impactful in making National Quantum Mission a grand success. With that, we are nearly end of today's engaging and insightful session. In the interest of time, I think we'll have to skip audience questions. Maybe students can write to both the speakers directly, or they can even write to us at events-nqm@iitk.ac.in. So as we conclude, we can say quantum computing isn't just another upgrade. It's the dawn of a new way of thinking, where uncertainty becomes the key to unimaginable possibilities. We extend our sincere thanks to our speakers for sharing their valuable insights on quantum computing and the research activities and opportunities at the Quantum Computing T-Hub. Thanks to the fellow moderators, the entire MCC team, and our wonderful audience for making this session a grand success. Stay connected on our social media platforms for future updates. And recording of today's session will be available on our LinkedIn page as well as it will be uploaded on our YouTube channel. Thank you all for joining us today.
So thanks
Thank
to
you,
everybody.
Professor Saptarshi, and thank you, Professor Chandrashekar.
Thank you. Thanks to the moderators and for the questions, giving us an opportunity to share what we do in lab and how we see for the future.
Thank you, sir.
Thank
It
you.
was our
Thank you.
privilege that you got the. Thank you.
Thank you.